Hi, everybody. Welcome to the CanDIG Mini-Conference of April 2022. This month, we're being treated to presentations by our cohort of co-op students from the University of Waterloo. This winter was our first time welcoming 3 co-op students at once, and we greatly benefited from the energy, curiosity, and talent that they carried into our projects and team dynamics. We're deeply grateful for their contributions and their company, and today we are excited to attend their presentations of their work. Please join me in welcoming Ali Razazadeh, Laiba Zaman, and Niharika Srivatsa to the stage with a round of applause reacts. Thank you. Next up, we're going to be treated to a discussion of differentially private federated learning by Laiba Zaman. Laiba is a third-year computer science student at the University of Waterloo. She was previously a student of health science and is interested in computational strategies for healthcare, as well as machine learning and cybersecurity. In addition to enabling complex cross-data type queries, as Ali just explained, the GraphQL interface permits the training of federated machine learning models on the CanDIG data services. Laiba worked closely with Ali to implement an experiment on CanDIG's federated learning services. We greatly benefited from her ML fundamentals and data analysis methods. Additionally, Laiba was responsible for developing the Vault Helper tool, a command line interface for modifying user permissions in HashiCorp Vault. Over the past 4 months, she has approached every single challenge with zeal, and her accomplishments reflect this attitude clearly. Please enjoy her presentation on differentially private federated learning and the Flower FL framework. And Laiba, let me know if you have any sharing issues, and I can pull up your presentation as well.
Okay, sounds good. You guys can hear me, right? It's typically my microphone, but okay, great.
We hear you.
Okay, awesome. Yeah, so I'll be talking about the federated learning repository, starting off with some background on federated learning. I won't delve too deep on it because it has been presented in a mini conference before. I'll speak about the overall structure of the repository and the experiment that we did on the Cynthia data set, and how to add a new experiment, and then speak about differential privacy and how it was currently implemented, and mention some next steps. And before beginning, I would like to mention that the work here was done in collaboration with Ali and with help from Yuri, and is based off of some of the work done by Rashab in his previous work term. And if you have any questions or feedback, or you see any errors, feel free to jump in or mention it at the Q&A session at the end. Also, if you feel if I'm not pacing myself well, you can feel free to jump in and mention that as well. All right, so just some background on federated learning. The way that traditional ML models work is that the nodes send data to a central server, which then applies the machine learning model to the data. Federated learning doesn't do this. It sends a model to the local nodes, and instead, and those local nodes train the model on the data set and then send it back to the server to be aggregated. It is aggregated on that server using the federated averaging algorithm, and that final model is what's used. One of the benefits of using federated learning is that the model doesn't leave the site, and this is particularly useful for our use case in healthcare, where laws in different provinces might vary. And because the model is trained locally, it allows for real-time predictions and less lag, and also lower latency with the models. Specifically for federation services like smartphones, it lessens the amount of hardware. And going on to the structure of the repository, there is an experiments folder that houses all the experiments done on the on the federated learning service, and the ingestion scripts just ingest data from Katsu. The orchestration scripts folder can be used to create appropriate Docker Compose files, like modifying the number of clients. And the services folder just hosts the submodules for Katsu and GraphQL, and then houses the client and server folders as well. In the client folder, essentially what happens is that we initialize the data set into a training and testing data set using the load data function. And then we set the initial parameters to be 0. And then we start the Flower client. In the FL server, there's a server.py file, which essentially sets the initial parameters of the model, and then uses this get evaluation function to perform in the strategy class to perform some server-side evaluation. And we call FL server.start server just to start the server for Flower. For this experiment on the Cynthia dataset, we used the 10 years female oncological dataset provided by Cynthia. And this is this hosts information about breast cancer patients and mentions things such as the stage of their cancer, their age, and the number of radiation sessions. And we chose the inputs and outputs based on some preliminary exploratory data analysis. The inputs are mentioned here, and the outputs were just chosen to be the stage of the cancer that was detected. So we did a non-federated experiment on this, and we did a federated experiment. The federated experiment has this following structure. It has an experiment.py file, a flower client.py file, a strategy, model, and settings. For settings, this is just used to house all the contents. The model is just houses the model. The strategy is it just uses the strategy that was implemented by Flower, and the only modification is that it saves the aggregated weights to a .npc file every 10 rounds. And I can, the sort of focus of this this part would be the Flower client and the experiment.py file. This experiment.py file has a few public classes which can be used if you want to add another experiment. So this just applies the pre-processing functions and then creates a data set split. The get model parameters is used to get the model parameters. The set model parameters sets the model parameters, and the set initial parameters sets all the initial parameters to be 0, since the parameters are uninitialized until model.fit is called. The Flower client.py file is used, has 3 public methods as well. These are used, this get parameters method is a convenience method for the client to receive a model's parameters so they can use that back to the server.
Sorry to interrupt you, Laiba. Are you trying to show us some code in a different window? We're still seeing the mini-conference presentation window.
Oh, I see. Sorry. Let me
All right.
just share this. Yeah, do you see it now?
Yeah, perfect. Thank you.
Okay, yeah. So this load data function just pre-processes the data and creates a data set split. This sets the model gets the model parameters. This method sets the model parameters, and this function set initial parameter sets everything to 0 for Flower to use because it's uninitialized before model.fit is called. And the Flower client has 3 methods. So the get parameters, the fit, and evaluate. Get parameters just returns the parameters for the Flower client, and the fit method just applies the model, fits the model to the data, and the evaluate method returns the loss and any type of other metrics of evaluation that you want. I'm going to go back to my screen. Just let me know if you can see it. Second.
Yep.
Okay, awesome. So to run the experiment, you would just run, you would start the quick start script with the different options. So there's the option to ingest, change the number of ports, the sites and the rounds, etc. And I can probably show you the output as well. Sorry, that was this was not a good idea. 1 second. Yeah, so as you can see here, there's some of the outputs of the experiment. So you have the accuracy, the F1 score, and the Matthews correlation coefficient. And this is done every single round. So you have a ton of different scores. And then in order to add a new experiment, as I mentioned before, you would need a settings.py file to have all the constants. The init.py file would stay the same as the Cynthia dataset. The model.py file would be where you add the model. If you wanted to modify the strategy.py file, you could do that as well. Otherwise, you would just have to override the the abstract methods in the Flower client and experiment.py. Thanks to Ali, who came up with a clever solution to allow for injected experiments. And one of the issues that this federated system has is is the fact that the model can memorize the specific data, especially if it's something like a neural network. So one way to remedy this is to use differential privacy. So differential privacy can add protection by injecting noise when training in the gradients or after training on the parameters of the model. A differential privacy algorithm ensures that an individual's data in the dataset cannot be extracted by the output of the algorithm. This then ensures that any two models trained on very similar datasets would be almost identical. There are two parameters to consider for differential privacy: the metric of privacy loss, which is the privacy budget, and the accuracy. Differential privacy also guarantees that the raw data won't be viewed, and if an attacker or an adversary has some auxiliary information, then it won't increase the effectiveness of their attack. And it's also resilient to post-processing, so a person cannot just simply increase the privacy loss by thinking of the output of the differentially private algorithm. There are a few differentially private algorithms that we were considering when selecting an algorithm, but they were not ideal since most differentially private algorithms inject noise to the clients of the federation instead of the individual data points, as they have many different clients, and that is suitable for them. However, each of the individual data points and experiments, such as the Cynthia Xcode oncological data, are individually sensitive, which is not addressed in these algorithms. The ideal algorithm would be this algorithm right here that was detailed by Tatarkis in their thesis. This algorithm combines this following algorithm with the federated averaging algorithm. And this algorithm right here computes differential privacy at the data point level. It does this by computing the gradient, by taking a random sample, and then for each example in that gradient, in that sample, it computes the gradient and then clips it based on a threshold C. This is to impose an upper bound to the sensitivity of the algorithm. And then the gradients are averaged and the noise is injected. This, in combination with the federated averaging algorithm, creates this final algorithm that would be ideal to use. However, since we did not have enough time and implementing this algorithm would require a lot of legwork, like modifying the server class and the strategy class in Flower, we instead chose to use diffpriv-lib. Diffpriv-lib applies differential privacy on the training data when applying the model. So the only modification is using diffpriv-lib instead of scikit-learn and NumPy. The researchers at IBM, when creating diffpriv-lib, had scikit-learn and NumPy in mind, so that way anyone who uses scikit-learn and NumPy can very easily use diffpriv-lib. And as a consequence, there are a lot of default parameters, such as the epsilon, which you can modify. One second. There are other ways to implement this, like we could use Abacus and Flower, but this uses PyTorch. It's detailed in this article below. PyTorch is more useful for deep learning and neural networks, so it wasn't ideal for our implementation. An alternative would be to override the strategy class and the server class and use the algorithm proposed by Tatarkis. And yeah, that's it for my presentation. Are there any questions?
I have a question if nobody else is super eager. Oh, awesome. Let's ask Javi first.
So hi, Laiba. Thank you for your presentation. So honestly, like, I don't know if I missed it, but I just wanted to know, like, can you comment on any like insights or anything that came out of the actual ML analysis, like out of the data that you analyzed? Were there any? Doesn't have to be very in depth, but any comments on like anything interesting that you found, or yeah, that's
yeah. If you want, I can actually go in and show you some of the exploratory data analysis that we did. Just give me 1 second. So yeah, so we found that, I can't seem to open this, sorry. Yeah, so we found that we using things like, there were, I think the medications were in as separate categories. So they labeled every single medication that was used by an individual. So instead of using all of those medications, we just aggregated them and just counted them as numbers. And that seemed to improve the accuracy of the model as well. And in terms of the most important inputs, those would be the primary tumor category and the regional nodes category. And I think there was one here. There was a bit of exploratory data analysis here. So this correlation heat map would show like the impact of stage and how correlated the inputs are. And we found that either taking away or adding other inputs did not impact it, or either decrease the efficiency of our classifier. So we implemented a logistic regression classifier and it was quite accurate. And we used this following stuff as input and the stage as the output, because I believe every single data point in that data set, everyone had cancer already, so it was more so to predict the stage of the cancer.
Okay, sounds good. Thank you.
Awesome. Thank you very much, Laiba. I will save my question to ask you in person for the sake of time.
Mhm.
Thank you very much for your presentation.